We are surrounded by patterns. They are everywhere we look, from the smallest details in nature to the vast expanses of the cosmos. Patterns are not just random occurrences, they are the building blocks of our world. They are woven into the fabric of our universe. The stars in the sky, the branches of trees, and the intricate designs of spider webs all follow specific patterns that can be observed and studied. Look closely at a sunflower. Its beauty is not just in its vibrant color but in the way its seeds are arranged. You'll see a spiral arrangement of seeds. This isn't just a random pattern, it's a precise and efficient way to pack seeds. It follows a mathematical sequence known as the Fibonacci sequence. This sequence appears in many places in nature, from the arrangement of leaves on a stem to the branching of trees. This sequence is called the Fibonacci sequence. It is a series of numbers where each number is the sum of the two preceding ones, often starting with 0 and 1. These patterns aren't just beautiful, they hold deep secrets. The spiral of a nautilus shell and the intricate designs of fractals reveal the underlying order of the natural world. These secrets can unlock mysteries of the cosmos. By studying patterns, scientists can gain insights into the formation of galaxies and the origins of the universe. They can help us understand the world around us. Patterns in data can reveal trends and correlations that might otherwise go unnoticed. One such intriguing pattern is hidden in numbers themselves. It's called Benford's law. This law states that in many naturally occurring collections of numbers, the leading digit is likely to be small. It reveals a strange truth about the digits that make up our world. For example, in many datasets, the number 1 appears as the leading digit about 30% of the time, while larger digits appear less frequently. It's a testament to the elegance of mathematics. This unexpected pattern shows how numbers and nature are intertwined in ways we are only beginning to understand, and it has some surprising applications. Benford's law is used in fields like forensic accounting and fraud detection, where it helps identify anomalies in financial data. In the early 20th century, an astronomer named Frank Benford made a curious observation. While working with logarithm tables, he noticed something peculiar. He was flipping through his book of logarithm tables, a tool essential for calculations before the advent of modern computers. He noticed that the pages at the beginning were more worn out, indicating they were used more frequently. This meant that numbers starting with 1, 2, or 3 were more common. Intrigued by this pattern, Benford decided to investigate further. He analyzed data from diverse sources ranging from physical constants to demographic data. He looked at river lengths, baseball statistics, and even the surface areas of lakes. He also examined numbers in newspaper articles, population figures, and death rates. Amazingly, the pattern held true across all these datasets. No matter the source, the first digit was more likely to be small. Lower digits appeared more frequently as the leading digit, with the number 1 appearing most often. This wasn't just a coincidence. Benford realized there was a deeper mathematical principle at play. There was a law at work, a law that would later be named after him, Benford's law. This law states that in many naturally occurring datasets, the first digit is likely to be small. Specifically, the digit 1 appears much more frequently than any other digit. The digit 1 appears about 30% of the time, which is significantly higher than the expected 11.1% if all digits were equally likely. On the other hand, the digit 9 appears less than 5% of the time, making it the least common leading digit. This predictable distribution of leading digits is now known as Benford's law. It has profound implications in fields ranging from fraud detection to data science, proving that sometimes numbers tell a story all their own. Benford's law isn't just a mathematical curiosity, it has real-world applications in various fields. Financial analysts use it to detect accounting fraud. Fake financial data often doesn't follow Benford's law. Population figures of towns and cities also tend to follow this law. Scientists use it to analyze data sets. They can identify errors or anomalies. Even in digital forensics, it helps analyze digital images for signs of manipulation. Benford's law is a versatile tool. It helps us make sense of the vast amounts of data in our world. Section 4. Deciphering the math. In this section we will delve into the fascinating world of mathematics that underpins Benford's law. This law, which might seem complex at first glance, is actually grounded in some very fundamental mathematical principles. The math behind Benford's law is surprisingly simple. It involves logarithms, which are a fundamental concept in mathematics. Logarithms help us understand the relationship between numbers in a unique way. Logarithms are the inverse of exponents. This means that while exponents deal with multiplying numbers, logarithms help us break down those multiplications into simpler, more understandable parts. They provide a different way to look at scales. Instead of seeing numbers grow linearly, logarithms allow us to see growth in a more compressed, manageable form. This is particularly useful in understanding phenomena that grow exponentially. Think about it this way. Imagine a company's revenue growing at a constant rate. If you plot this growth on a regular scale, the numbers can quickly become unwieldy. But on a logarithmic scale, the growth is much easier to visualize and understand. It takes less time to go from $1 million to $2 million than it does to go from $8 million to $9 million. This is because the percentage increase is the same, but the absolute numbers are different. This concept is crucial in understanding Benford's law. The law states that in many naturally occurring collections of numbers, the leading digit is more likely to be small. For example, the number 1 appears as the leading digit about 30% of the time, while larger digits appear less frequently. This natural growth pattern, when translated to digits, results in more numbers starting with 1, then 2, and so on. This is because smaller numbers are more likely to occur in the early stages of exponential growth. The logarithmic scale explains why lower digits appear more frequently as the leading digit. By understanding this, we can better grasp the underlying principles of Benford's law and its applications in various fields, from fraud detection to data analysis. Section 5. The enchantment of Benford's law. What's truly fascinating about Benford's law is its counterintuitive nature. We expect digits to occur with equal frequency, but the universe doesn't always play fair. This law reveals a hidden pattern in the seemingly random distribution of numbers. This pattern appears everywhere. It emerges in physical constants, stock market prices, and even the lengths of rivers. This universality makes Benford's law all the more intriguing. Its practical uses, particularly in fraud detection, make it a powerful tool. By understanding this law, we gain a new lens through which to view the world. Section 6. Where Benford's law falls short. While Benford's law holds true for a wide range of data, it's not universally applicable. It has its limitations. For instance, data sets with fixed ranges like telephone numbers or lottery results don't follow this law. This is because the leading digits are predetermined. Human-created numbers, like assigned ID numbers or prices set at psychological thresholds, also deviate from this pattern. These numbers are influenced by human biases and intentions. Understanding these limitations is crucial for applying Benford's law effectively. Section 7. The universe speaks in numbers. Benford's law serves as a reminder that the universe is full of surprises. It shows that even in the seemingly mundane world of numbers, there is beauty, order, and wonder to be found. This law beckons us to look closer, to question assumptions, and to marvel at the intricate patterns that govern our world. It encourages us to embrace the power of mathematics. It helps us unlock the secrets of the cosmos. So the next time you encounter a set of numbers, remember Benford's law. You might just uncover a hidden message within the digits.